All right, I think we're recording now. So there's a lot to say about the final. One of the things that you can see is I have posted the first page of the final exam. Of course, the first page doesn't actually have any questions on it, but it has the instructions, and you can learn a lot by looking at this. For one thing you can learn, this is a very short final. This is the shortest calculus final, as far as I know, for the last decade. Only 6 problems long. You're probably saying, aha, well, they probably made like all 6 problems have multiple parts. No, 2 problems have multiple parts, but even those multiple parts aren't that bad. This is not a test which should take you 2 hours. And we did that deliberately, or at least I did, because I know some people have another final immediately after, and we don't want to drain your mental energy. And so if you prepare, it's quite reasonable to finish the test in an hour, and it's very reasonable to finish in an hour and a half. And if you're going past an hour and a half, you're welcome to do that. You got 2 hours for the test, but it's not clear if you're going to make much more progress. Calculators are allowed. It's like the midterm. Any calculator you want, you can use it. You don't need it. So at best, you just need a calculator to double check your addition and multiplication. But if you want to use a graphing calculator, you can use a graphing calculator. Make sure you answer each question using exact values, because it says it right here, and it bolded and it underlined. I don't know how we could have made it even more clear than that. You don't have to simplify your answers. If you're doing a convergence test, tell us which test you're using. We want to make sure that you're applying the correct test and that what you're doing is done correctly. Show your work legibly, and if you have answers without work, well, you won't get credit. So that includes saying, I set up this integral, and then all of a sudden here's the answer. Well, then you don't get the credit for doing the computation. Your calculator did it. We're testing you. Can you carry out the computations? There's nothing too incredibly hard about this. Okay, so that's the first page of the exam. Make sure you know where to go. It will probably be different from where your classroom is. You have a review sheet, and it has a lot of basic information about the final. Some other things that we should point out: this is not comprehensive. We're testing you on what you've learned since the midterm. So in other words, you don't have to know about trig substitution or integration by parts. We're not doing that. We're focusing on Chapter 10 and Chapter 11. About the only topic which overlaps are improper integrals. In other words, integrals which involve infinity, because we needed it for a few cases in the latter part. And test is at 2:15. I encourage you to arrive early. You don't get any notes, but you can study beforehand. We will give you 1 blank page for scratch paper, and that should be sufficient. Keep in mind that this is being group graded, which means that the people who have been grading you most of the semester are not the people who are grading your final. So what does that mean? Well, be clean. Write legibly. And while we're talking about writing legibly, please write your name legibly and your full name. You're probably saying, wait, people don't do that? No. Write your name legibly. It's very hard sometimes for us to figure out who took the test. But okay, write legibly, be organized, go through it step by step, circle your answer so we can find what you're looking for, and the important thing, of course, is avoid making mistakes. No big surprises here. Make sure you check your work. Nothing is crazy. All the answers are nice. Some of them surprisingly nice. So if you're getting like these hideous answers, you should be very skeptical of what's going on. Make sure you have plenty of rest. Make sure you know your trigonometry. This is really important, especially when we get into polar coordinates. You need to know your trigonometry. You don't need to know many obscure identities. I would strongly encourage you to know power reduction, because that happens frequently when you're working in polar coordinates. I listed the basic integrals up here, and there's no real surprises, but I want to point out that literally the only integrals that you will be asked to do are written here. If you have an integral that is not up there with those basic integrals, you have made a mistake. That, or that you still have some simplifying that you can do, or there's a substitution. You're not going to get anything which is not a very basic integral to work with. So that's not a very long list. I just want to emphasize this because the point here is we're not trying to be crazy. These should be fairly, hopefully, we're hoping, straightforward problems, which you should have some fun with. I hope you enjoy it. I hope you enjoy it. We had fun writing it. Then the rest of this is review. And it's a nice summary. And pretty much, if you know how to do all of these things on that remaining page and a half, you'll be good to go. Okay, any questions before we jump into doing problems? Any questions about the final? All right, well, I will say I wrote it. So I'm pretty knowledgeable about what's on it. If you're trying to guess, I know what kind of problems he likes, so I know what to study. I'll warn you, I wrote the test, but I only got to pick 5 out of the 6 problems. 1 problem was picked for me. So that doesn't mean, well, interpret that however you will. Interpret that however you will. Okay, well, with that, we will go straight into our 22 problems. And so we'll start with number 1. It's a good place to start. So find the exact value. Now here's the great thing about exact value problems. If you ever have a problem that says find the exact value, there are only 3 things that you can do. And 3 is a very small number. So what are the 3 things that we might see? Well, you might see geometric. That's something we might see. We might see telescoping. Now what does that mean? Telescoping are sums which cancel. In other words, your nth term cancels with part of your n plus first term, and so forth and so on, so everything collapses. And the other thing you might see are Taylor series. So that's it. If you're ever asked to find the exact value, you know automatically you have to do one of those 3 things. And so you have to say, which mode am I in? So on this problem, we're asked to find the following. The sum n equals 0 to infinity of 2 to the n plus 3 to the n over 2 plus 3 to the n. Now, some people in their rush will say, oh, 2 plus 3 to the n, that's probably 2 to the n plus 3 to the n, and I'm adding up 1. Because I get 2 to the n plus 3 to the n over 2 to the n plus 3 to the n. Okay, no. Be careful. Be careful. So this is the sum, n equals 0 to infinity, of 2 to the n plus 3 to the n over 5 to the n. Now here, I'm going to point out a very cool fact. Do you see this right there, that plus sign? That plus sign says, break it up into parts. So, what can we do? That's the sum, 0 to infinity, of 2 to the n over 5 to the n plus 3 to the n over 5 to the n. And now, what can I do here? Well, I say, well, look, this looks geometric. If I cover up one part, I get 2/5 to the n. If I cover up another part, I get 3/5 to the n. And I say, well, can I break it apart? And the answer is yes. Sums break apart nicely. Sum n equals 0 to infinity of 2/5 to the n. That's the first part, plus the sum n equals 0 to infinity, 3/5 to the n. And now we see, we are geometric. So the first sum is 1 over 1 minus 2/5, and the second sum is 1 over 1 minus 3/5. Why? Well, the sum from n equals 0 to infinity of a r to the n is equal to a over 1 minus r. In our case, a was 1, and then r was 2/5 and 3/5 respectively. Well, okay, this is not so bad. 1 minus 2/5 is 3/5, and you flip it, that's 5/3. 1 minus 3/5 would be 2/5. You flip it, that's 5/2. 5/3 plus 5/2. Common denominator would be 6. So that's 10 over 6 plus 15 over 6, giving us a final answer of 25 over 6. Good. Well, let's hope for one of those. Those are fun. Okay, well, let's try something a little different. All right, find the exact value of the following. 3 times 9n squared plus 15n plus 4. Now, I can look at this and say, it's not geometric, because there's no power. Geometric is something to the n power. So that's not there. So I know it's not geometric, and it doesn't look like any Taylor series that I recall. So I say, well, maybe it's telescoping, because again, I'm in my exact value mindset. So telescoping, one of the things that often happens is some kind of partial fractions. So I ask, can I factor my denominator? So I look at this denominator, say, well, can it factor? And maybe it can. Let's see, 9n squared. Well, I have to have two numbers that multiply together to give me 9. But because I'm leaning towards geometric, I probably should have them be more or less matching. So 3n and 3n. And if you think about it for a while, you can convince yourself that what works is 3n plus 1, 3n plus 4. Now, if you don't like that, you can, of course, take more time. You can use quadratic formula, find roots, and so forth and so on. And you can check. You do get 9n squared. Also, 12n plus 3n is 15n plus 4. Okay, so that works. So really, this is the sum, n equals 0 to infinity, of 3 over 3n plus 1 times 3n plus 4. And as a general rule of thumb, a lot of what we're going to have you do is we're going to give you a problem which requires you to think about it a little bit and perhaps think about how you can rewrite it. All right, well, let's do our little bit of rewriting here. 3 over 3n plus 1 times 3n plus 4. Partial fractions, a over 3n plus 1 plus b over 3n plus 4. Clear my denominators. 3 would equal a times 3n plus 4 plus b times 3n plus 1. And now at this point, there's a couple of techniques. You can expand and group coefficients. Some of you probably learned it that way. I like to say, what's a good choice for n? And you're probably thinking, well, like n equals negative a third would be a great choice here, but negative 1/3 is not a whole number. Am I allowed to do that? Am I allowed to put something that's not a whole number? And the answer is yes, you can do that. It doesn't matter. So, for instance, I say if n equals negative 1/3, then the second part drops out. All right, well, what happens? The first part would be what? Well, I have 3 times negative 1/3, which is negative 1 plus 4. So I get 3 equals positive 3a. Or a equals 1. Okay. What's another good choice? Negative 4/3 is a great choice. Why? Because if I choose negative 4/3, now the first term drops out. Well, negative 4/3 times 3 will be negative 4 plus 1 is negative 3. 3 equals negative 3b, or b equals negative 1. They'll always work out very nice when we have these types of problems. Getting back to our sum. So we now have that this is equal to the sum of, well, let's see, it's a 1 over 3n plus 1, and then b 1 over 3n plus 4, and n equals 0 to infinity. All right, now it depends how rigorous we want to be at the next step. But you know, I'm not going to really worry about rigor, and so this is what I would do. I would say this is the following. Let's start by writing the first few terms. I'm going to get 1 over 1, because I'm putting in n equals 0, minus 1 over 4. And then I go to the next term, put n equals 1. I'll have 1 over 4 minus 1 over 7. Then the next term, well, I'll put in n equals 2. 1 over 7 minus 1 over 10. And so forth and so on. 1/10 minus 1 over 13. and dot, dot, dot. But the point here is that we get cancellation. In fact, we get this long string of cancellation. Everything cancels. Cancel, cancel, cancel. And what doesn't cancel? Well, what doesn't cancel is the very first term, which tells us our answer is 1. And that's it. Now, if you're somebody who likes rigor and says, look, I really insist, I want rigor. Well, the way you would do that, and you don't need to, but since I somehow have this ongoing internal discussion with myself, what you would say is look at the partial sums, because infinite sums are really just partial sums where the top goes to infinity. And here, if you do the cancellations, what you'll see is that you'll get the first term and you'll get the last term. And everything else cancels in the middle, and then you say, aha, this part goes to 0. So that would be if you were doing it more rigorously, but again, don't worry about that part. All right, well, 2 exact value problems down. That's pretty good. We're making good progress, putting a good dent. Now, we should finish. Get the trifecta. So we've done one which had geometric. We've done one which had our telescoping. Now we should do one which ties to Taylor series. So here, sum n equals 1 to infinity, 1 over n, 2 to the n. Now it almost looks geometric, but this n here tells us it's not geometric. So we say, okay, it's not quite geometric. But what you can do, and it's a good way to think about it, when you see these types of expressions, we say, well, look, this is really the sum of 1 over n times a half to the n. So in other words, whenever I see whatever to the nth power is, I'm going to think of that as something to the n. And now I say, all right, have we seen anything that looks like this type of thing? In other words, have we seen anything that looks like sum n equals 1 to infinity, 1 over n, x to the n? So in other words, I'm trying to connect to a Taylor series. And, well, have we? Well, yes, we have. Recall 1 over 1 minus x, that's the sum from 0 to infinity, x to the n. Now you're probably saying, okay, that was the wrong guess because this has a 1 over n. Well, I'm not done yet. Integrate both sides. Integrate 1 over 1 minus x, that's negative log 1 minus x. Yes, the negative comes from the fact that you have to compensate for the negative in the minus x. Well, that's the sum, n equals 0 to infinity, of x to the n plus 1 over n plus 1. But through reindexing, which is a fun little fact, this is the sum n equals 1 to infinity of x to the n over n. And we say, ah, look, it matches. So what do we have? That says that our original sum, this is really a log. What log? Well, minus log of 1 minus a half. Okay, well, we can clean that up. 1 minus a half is a half. And then the minus lets you flip it. So 1/2 flipped becomes log 2. And there's the answer, log 2. All right, good. Well, I'm guessing that's the end of our find the exact value examples because we've done all 3 different possibilities. Don't worry, there's lots of more problems coming. Number 4, determine if the following series converges conditionally, converges absolutely, or it diverges. Well, let's make a note. Cosine pi over n is a secret way for us to say negative 1 to the n. Oftentimes, if we're trying to hide a negative 1 to the n, we can do it by using the cosine function, because cosine of 0 is 1, cosine of pi is negative 1, and I alternate 1, minus 1, 1, minus 1, so forth, and so on. So really, we're not going to be misled. We really know this is the sum n equals 1 to infinity of, well, what? Negative 1 to the n log of n divided by n. Good. Now, we notice something. We have an alternating series. And we say to ourselves, well, there's a test for alternating series, and the test is called the alternating series test. That's easy to remember. If you have an alternating series, use the alternating series test. Okay, well, what do we need to check? Well, alternates, good. Check, and terms go to 0. And we just note that log n over n goes to 0, and we'll trust you. We'll trust you. Okay, so check. So now I'm done. I've verified everything I need for the alternating series test, so series converges. Now, unfortunately, we're not done, because there's two ways you can converge. All we've really shown is that it's not this third option. It's not diverge. It's going to converge. But the question is, does it converge conditionally, or does it converge absolutely? So to answer that, we go into sort of phase 2. So because we have an alternating series, now we say, well, what would happen if I dropped the absolute value? If I dropped the alternating. So in other words, I'm going to look at the sum of the absolute value of the terms. So here I go. Well, again, as I said, that's really just looking at the sum log n over n. Now, at this point, what do we do? Well, there's a couple of options. Here's something we can do. Option 1. Well, we can do comparison test. What does that mean? Well, log n over n is bigger than or equal to 1 over n for n at least 3. Because log of n is at least 1. Not a very big surprise. What do I know about the sum of 1 over n? Yeah, and the sum of 1 over n diverges because it's a p-series. P-series, p equals 1. So, sum log n over n diverges. So in other words, I can compare it. I can bound it below by something which diverges, so it must also diverge. Now, that's option 1. It's good to keep all your options on the table. Here's option 2. We can do the integral test. What's the integral test? Well, let's look at the function log of x over x. And we'll integrate that. 1 to infinity. Now, why? Because log x over x is a lot like log n over n, but it's a continuous function. And we can tie the two questions of convergence together. Does the integral converge? Does the sum converge? The answer will be the same. So, well, what do we have? What is the integral of log x over x? You let u equal log x. Du would be 1 over x dx. So this becomes the integral 0 to infinity of u du. Well, that's a half u squared from 0 to infinity, and that's pretty big, infinity. Okay, so since the integral diverges, the sum diverges. All right, so both work. Which one do you have to do? The answer is either one. Look, we're not saying that you have to use a certain test. Use whichever test you like. There are oftentimes multiple tests that work. Try to use an efficient test. That'll make everybody much happier. But let's go back to our original problem. The question was, what's happening? Well, because the sum converges itself by alternating series test, but the absolute value fails to converge, well, that says we converge conditionally. Because we need the sign. The sign was important. All right, there we go. Let's do a different one. Determine if the following series converges conditionally, converges absolutely, or it diverges. Now, right away, we notice that all the terms are non-negative. So before we even start, we know that we can eliminate this option. It cannot be a converge conditionally because there's no negative involved. If there's no alternating sign, then it's either it converges absolutely or it diverges. There's no conditional. Okay, so now we're going to focus on the question about whether it converges or diverges. You'll notice something here. There is an exclamation mark. And if you ever see an exclamation mark and you're asked about convergence or divergence, you should say to yourself, I don't know why I'm writing this down, but you should say to yourself, I should try ratio test. Because ratio test is fantastic for factorials, and pretty much if you have a factorial, nothing else works. So if you're ever asked about convergence and there's a factorial involved, pull out your ratio test. So I'm thinking of a sub n. That's my n to the 3n over 3n factorial. And now I'm going to do my ratio. So what does that mean? I'm going to take the limit as n goes off to infinity of a sub n plus 1 over a sub n. I don't need to worry about absolute values because, as I already said, these terms are not negative. All right, so this is the limit as n goes to infinity of, and here's where we have to be careful, m plus 1 to the power 3 to the n 3 times n plus 1 over 3 times n plus 1 factorial, all divided by n to the power 3n over 3n factorial. Okay, now this problem will probably test us on our ability to rewrite various expressions. So limit as n goes to infinity. So what do I mean by that? Well, here I have n plus 1 to the power 3n plus 3. So I'm going to think of that as n plus 1 to the power 3n times n plus 1 cubed. So that's my n plus 1 to the power 3 times n plus 1. And then downstairs, I'm going to have n to the power 3n. And I'm going to come back and focus on pieces later. I also have this 3n factorial, which will come up. That will be in my numerator. So 3n factorial. Then I have this 3n plus 3 factorial, which is in my denominator. Now, because I have this 3n factorial, I want to make them more or less compatible. So what I'm going to do is I'm going to pull off pieces from the front so that I can cancel a 3n factorial. So if I do that, I'm going to start just writing by saying, look, I have 3n plus 3 factorial. Well, I'm not to 3n yet, so I'm going to start 3n plus 3. Let me write my next term. 3n plus 2, nope, not there yet. 3n plus 1, nope, but I'm getting close. 3n, yes, there I am. So this part, 3n plus 3 times 3n plus 2 times 3n plus 1 times 3n factorial, was just another way of writing 3n plus 3 factorial. Now, written in this way, what can we see? Well, we can see that the factorials will cancel. That's good. Progress, progress. Very important. Let's pause for a moment and think about this as really having two parts. There's a limit of n going to infinity. This first part I can write in the following way, because they're both to the same power. They're both to the 3n power. So I'm going to write this as n plus 1 over n. Well, really 1 plus 1 over n to the 3n power, which I'm going to write in a very strange way, n cubed. And I'd claim, and you can convince yourself, you have a whole week to do that, that this part right here becomes that part right there. Then you also have in n plus 1 cubed over 3n plus 3 times 3n plus 2 times 3n plus 1. All right, now let's talk about these pieces. 1 plus 1 over n to the n power is something which you should know. What does 1 plus 1 over n to the nth power do? Oh my gosh, somebody saw a mouse. They said, E! Oh wait, no, that's the answer. It's E. So, all right, so that's E. Now, don't forget there's a cube there. So this part, this whole part, is going to go to e cubed at the start. On the other hand, let's think about this other part. Here, what do I have? It's a polynomial over a polynomial. They're both cubics. You factor it out, there will be an n cubed plus lower order terms on top. Downstairs, it'll be another n cubed times a constant. And so when you have polynomial over polynomial, you look at the leading coefficient. What's the leading coefficient? Well, upstairs, the leading coefficient is it's a 1. Downstairs, it's a 3 times 3 times 3, which is 27. So the ratio is e cubed over 27. Well, what do we know about e cubed over 27? We know e cubed over 27 is less than 1 because e is below 3. So e cubed is less than 27. So what have we done? We started with taking the ratio. We found the limit. The limit was below 1. So our conclusion is by the ratio test, if our limit is below 1, the series will converge. And because we know there's no negatives, it converges absolutely. And that's the answer. Absolutely. All right. Now, on a side note, if you did n to the power 2n over 2n factorial, it will diverge. So, 3 was a magic number. It converged at, when you had 3s, it would diverge if you had 2s. Okay, good. Well, now we come to one of our favorite types of problems. These are classics. You see these on many exams. It says the following. Determine the interval of convergence for the following power series. You have x minus 2 to the power 2n over n to the 4n. Now, for this case, when we do this, whenever you're looking for an interval of convergence, there's more or less 2 steps. Step 1, find the radius. And what does this do? It gives you really everything but the endpoints. So once you know the radius, you have all but the endpoints. Well, step 2 is figure out the endpoints. So that's it. So whenever you're finding interval of convergence, you always go through these 2 things. What's my radius? That gives me everything but what's happening with the endpoints. And then you say, okay, well, what happens with the endpoints? And for that, you have to be careful. Now, when you're finding the radius, you have to decide between ratio test or root test. And to make that decision, your rule of thumb is, look, if there is a factorial, you got to go ratio. But if everything is powers of n, go with root. Now, what about this n? Well, it's a coin toss. Both will work. In this case, let's do a ratio test. All right, so here we go, ratio test. So how do we find the interval of convergence? I'm thinking of this whole thing as my a sub n. So I'm going to take a look at the limit as n goes to infinity of the absolute value of an plus 1 over absolute value of an. Now, the reason I have absolute value this time is x minus 2. It could potentially be negative. So I want to be careful. All right, so this would be the limit as n goes to infinity of, let's go through here. The only place where I need absolute value is on that x minus 2. So it would be absolute value of x minus 2 to the power 2 times n plus 1. So I'll go ahead and write that. Oh, wait, why did I say ratio test? I don't want to do ratio test. Let's do root test. I'm sorry. I had to get up early this morning. I was out in Spokane, so I had to get back here. I want to do root test. Why was I writing ratio test? Okay, an to the 1 over n power. That would have worked, by the way. That would have worked. So, on a side note, if you're going to take the test, be well rested. Be well rested. Okay, absolute value. Okay, so this is absolute value of x minus 2 to the power 2n over n to the 4n, all raised to the 1 over n power, which is the limit as n goes to infinity of absolute value x minus 2. Now notice 2n to the 1 over n becomes squared over n to the 1 over n times 4 to the n to the 1 over n. That's just 4 to the 1. Now, the only place where n's are still showing up is down here in the denominator, n to the 1 over n. And that's one of the limits you should know. It's actually even written on the review sheet. N to the 1 over n goes to 1. So that this becomes x minus 2 squared over 4. Now, when you apply the root test to converge, you need this to be less than 1. So we need absolute value of x minus 2 squared less than 4. Or absolute value of x minus 2 is less than 2. Now we've found the radius. Let's start making this into an interval. So to drop the absolute value, what do? Well, I basically say if I'm below 2, that means I'm between negative 2 and positive 2. So negative 2 is less than x minus 2 less than 2. Then I add 2 because I want to get rid of that minus 2. So adding 2, that makes this 0 less than x less than 4. All right, now that's not our interval yet. It might be, but I don't know. What I have to do is I have to check the endpoints. We've now finished the first step. All right, so endpoints. So I have 2 endpoints. I've got to check both. So let's go ahead and pick 0 first. All right, so I plug in x equals 0. Now what do I mean come back to your original sum and plug in x equals 0. Don't bother with the root test. The root test won't tell you anything. You got to go and actually evaluate. So plug in 0. This will become the sum of negative 2 to the 2n over n 4 to the n. N equals 1 to infinity. But negative 2 to the 2n is the same as 4 to the n. There's another 4 to the n. So if you cancel and simplify, you get 1 over n. Well, what do we know about the sum of 1 over n? We know it diverges. Why? It's a p-series. So you should know your p-series and your geometric series. And if you plug in x equals 4, well, something similar will happen. Because if you plug in x equals 4 to your original sum, and you say, well, this becomes 4 minus 2, which is 2 to the 2n, over n 4 to the n. But again, 2 to the 2n is still 4 to the n. So sum n equals 1 to infinity of 1 over n. So again, diverges, p series p equals 1. And therefore, we include neither endpoint, because the sum diverges at both endpoints. And so, in fact, our interval was right. So our interval will be 0 less than x less than 4. And there we go. So there's our interval of convergence. All right. Number 7. Determine the interval of convergence for the following power series. 4 times x minus 1 to the n over n log n squared 2 to the n. Well, boy, okay, a little different. All right, and for some reason we're starting the sum at n equals 10. I don't know why, but that's okay. It doesn't matter. We can start it. Because convergence doesn't happen at the start. Convergence happens in the tail. So that's what we care about. So it doesn't really matter where we start. All right, so, well, I would, again, apply the root test. So I'm going to take a look at the limit as n goes to infinity of absolute value a sub n to the 1 over n. And so this is the limit as n goes to infinity. The only part that's negative here is that potentially that x minus 1. So I have 4 absolute value of x minus 1 to the n over n log n squared 2 to the n to the 1 over n power, which is the limit as n goes to infinity of 4 to the 1 over n, x minus 1 to the n to the 1 over n just becomes x minus 1. Then I'm going to have this n log n squared to the 1 over n. We'll talk about what happens there. Then I have 2 to the n to the 1 over n is 2. So let's talk about our pieces. Well, 4 to the 1 over n. This one trips a lot of people up. 4 to the power of 1 over n does what as n goes to infinity? Well, it'll go to 4 to the power 0. 4 to the 0 is also known as 1. So if you see a number and there's nothing attached to that number, that's not going to affect your interval of convergence at all. To the 1 over n power, or you take your ratio, it drops out. So look, it's going to just go away. It's going to go away. Now this is a little bit more subtle. You can say, well, look, I know n to the 1 over n goes to 1. I also know, same argument, n squared to the 1 over n goes to 1. So this will go to 1. I'll skip the details because they are not illuminating. But it does go to 1. Which tells us that we're left with absolute value of x minus 1 over 2. So I have that I need to have x minus 1 over 2 to be less than 1, or x minus 1 should be less than 2. Drop my absolute value, negative 2 less than x minus 1 less than positive 2. Now I add 1 to everything. Or I have negative 1 is less than x is less than 3. All right. So we have everything except the endpoints. So now let's focus on the endpoints. So we need both endpoints. Let's start with x equals negative 1. That should not be so bad. Then we have the sum from 10 to infinity of 4. Minus 1 is minus 2 to the n over n log n squared 2 to the n. So that's the sum, n equals 10 to infinity. Well, can we simplify? The answer is yes. I have two things to the n power, negative 2 to the n and a 2 to the n. Negative 2 to the n over 2 to the n becomes negative 1 to the n. So I have this 4. Again, the 4 won't affect convergence. I have negative 1 to the n, and I have over n log n squared. Now, at this point, we should pull out one of our tests. What test works here? Yeah, it's alternating, because I see that plus minus 1. And the other thing I know is that terms will go to 0. In other words, as n gets large, the denominator gets big, things go to 0. So if I'm alternating, my terms go to 0, I can conclude that this converges by the alternating series test. Okay, which means we include negative 1. Negative 1 is definitely part of our interval of convergence. But we're not done yet, because we have another endpoint. So now we plug in x equals 3. So we have the sum, n equals 10 to infinity. I've plugged in x equals 3, and I mean plug it into our original expression. So if I plug it into my original expression, I'll have 4. 3 minus 1 is 2 to the n, so 4 times 2 to the n over n log n squared times 2 to the n. Nice cancellation. So this becomes the sum, n equals 10 to infinity of 4 over n log n squared. And now, does this converge or does it diverge? Well, not so clear, not so clear. But that's okay. We have ways of figuring it out. Because it's not quite a p-series, because there's that log n squared factor here. But what we can do is we can do the integral test. So we'll pull out the integral test. 10 to infinity of 4 over x log x squared dx. Well, make our substitution. U equals log x. Du is 1 over x dx. Very convenient here. Very convenient. They might have said, how did you know to do the integral test? Well, because I wrote the problem. That's how I knew. But what if I hadn't written the problem? Well, what I would have said is, what would happen if I thought about this as, instead of n's, as x's? If I saw 1 over x log x squared, I would say, well, wait a second. If I did a substitution, u equals log x, du is 1 over x. Oh, wait a second, there's like a substitution set up here. And so sometimes you can do this mentally, just sort of say, what would happen if? And this is one of those times when you can do one of those what ifs. Okay, so if you carry out this integral, this would be the integral, do my substitution. So log x, so log 10, some number, log of infinity, well, so it goes to infinity. And then it becomes what? Well, it would become the 4 stays as the 4. The dx over x becomes my du. And log x squared downstairs is u to the minus 2. So that's not a bad integral, because that's a nice u to a power. That's on our list of things that we should know what to integrate. So this is negative 4 over u from log 10 to infinity. And the nice thing is at infinity, or when we say evaluate at infinity, we really say what's happening as I go to infinity. And as I go to infinity, this goes to 0. Goes to 0. So I have it 0 minus negative 4 over log 10. I really don't care about the value. I just care about whether it converges. So the integral converged. All right? Which tells us that the sum converges. Which tells us that at x equals 3, I also include that endpoint. So I'm including both my endpoints. And therefore, my final answer is that my interval is going to be from negative 1 less than or equal to x, less than or equal to 3. And there we go. That's our answer. That's our answer. All right. We're doing good, but we're going to have to pick up the pace if we're going to finish. Well, I can stay a little bit late. If you need to go, it's okay. I don't mind. I don't mind. Okay. Number 8. Show that 1 plus x to the negative 1/2 is the sum n equals 0 to infinity of negative 1 to the n, 2n factorial, x to the n over 4 to the n factorial squared. Of course, right? What else could it possibly be? Well, this looks bad, but it's not so bad. Why? Because this right here is one of our basic Taylor series that we should know. This is our binomial series. Remember, 1 plus x to the alpha is equal to the sum, k equals 0 to infinity of alpha, choose k, x to the k. All right? So what do I need to do? Well, I don't have to do very much, because I'm starting with this 1 plus x to the negative 1/2, and so I know this is equal to, I guess I'll go back to n's, so it matches what I have here, n equals 0 to infinity of alpha, alpha is negative 1/2, negative 1/2, choose n, x to the n. So really, what it says is that this part right here, somehow, I just have to argue that these are the same. So let's pause for a second and look at negative 1/2, choose n. Now, what does that mean? It says you start negative 1/2, and then you keep subtracting 1. So then the next term will be negative 3/2. And then the next term after that will be negative 5/2, and so forth and so on, all the way up until you've gotten to n terms. Now, how far will that get me? Well, the answer is that'll get me all the way to negative 2n minus 1/2. So just, for example, if n equals 1, I should start up at negative 1. If n equals 2, I should stop at negative 3. So 2n minus 1/2. Then downstairs, because of the way that these binomial coefficients works, that's an n factorial. Okay, well that's good. I can see I already have one of my n factorials, but this says you need a second one. So that's very suggestive. Now, let's see what we have. We have n terms, each has a negative, so this becomes negative 1 to the n. Each has a 2, so this becomes 2 to the n factorial. And then I have 1 times 3 times 5, all the way up to 2n minus 1. All right, so there we have that. Well, what can I do with that? This looks a lot like a factorial, except I'm missing terms. I'm missing every other term. So how do I solve that? Well, the answer is I put every other term back in. So I have negative 1 to the n, 1 times 2 times 3 times 4 times 5 times, go up to 2n minus 1. I'll even put in 2n just for fun. But if I add terms, I have to balance out. I'll balance out downstairs. 2 times 4 times so forth and so on, all the way to 2n. And then I say, well, wait a second. If I factor out a 2 out of each term, that's really 2 times 1, 2 times 2, 2 times 3, all the way up to 2 times n. This is 2 to the n times n factorial. And upstairs, this is 2n factorial. So I have negative 1 to the n, 2n factorial. Downstairs, I have 2 to the n times 2 to the n, which is 4 to the n factorial times n factorial is n factorial squared. And so I say, aha, negative 1/2 to the n, negative 1/2 choose n, this binomial coefficient, is the sum. Let's write this down. I can replace this binomial coefficient with this expression. Negative 1 to the n, 2n factorial over 4 to the n factorial squared. And then my x to the n. And I say, aha, exactly what we wanted. Now, you might be getting nervous, and you might say, would we be expected to do this on the test? Well, no, I really want to test you on part B. But this one is just too good not to show you. It's so cool. You got to see it at least once in your life. This was your once. If you're lucky, you'll get to see it twice. But really, we're testing on part B. Okay, part B. So, what do we have? Well, let's recall from part A, 1 plus x to the negative 1/2, we just found is this sum, n equals 0 to infinity, negative 1 to the n, 2n factorial, over 4 to the n factorial squared x to the n. And we're asked to find the Taylor series for arcsine. Now, what's true? Well, arcsine, if I take the derivative of arcsine, I get 1 over the square root of 1 minus x squared. Well, you'll notice 1 over the square root of 1 minus x squared is actually very close to this, because this is really 1 over square root of 1 plus x. Now, one of the things you have to get used to is the idea of these series being malleable, changing the name. So what I can do is I can say, let's go into this series, and what I can change is everywhere I see an x, I put negative x squared. So this would become the sum, n equals 0 to infinity of negative 1 to the n, 2n factorial over 4 to the n factorial squared. That doesn't change because there's no x. I'm only changing the x part. Now the x part, that changes, because what have I done? I replaced negative x squared where I had x before. So negative x squared to the n. Now here, you'll see that, lo and behold, I have a negative 1 to the n, and then I'll have another negative 1 to the n. The two negative 1s to the n come together, and they cancel. So the negative 1 to the n's gone. So it's 2n factorial upstairs, 4 to the n factorial squared, x to the 2n. Now, that we're not done, that's not arcsine, that's 1 over square root of 1 minus x squared. But there was a hint. That's got me to work on 1 over square root of 1 minus x squared. The derivative of arcsine gave me this expression. If I integrate this expression, I'm going to get arcsine. So I can say that arcsine of x, and the nice thing about arcsine of x is arcsine of 0 is 0. That's the integral. Sum, n equals 0 to infinity of 2n factorial over 4 to the n factorial squared times x to the 2n dx, because I'm just integrating. And the key here is to say, look, if you have an integral, you integrate term by term. So sum 0 to infinity, I'm going to have 2n factorial, and I'm going to have 4 to the n factorial squared. Now when I integrate x to 2n, that becomes x to the power 2n plus 1. Add 1. Then I divide by my new power, so I'm going to divide 2n plus 1. And that's the answer. So there's the Taylor series for arcsine. So we can do arcsine. Ah, beautiful, beautiful. No, you don't have to memorize the Taylor series for arcsine, because you can always just rederive it. It's easy, easy, right? All right. So, number 9. Find p sub 2 of x. Oh, let me pull this down. The Taylor polynomial of order 2 for f of x equals e to the power x to the 3/2 minus 1, centered at x equals 1. Now, there's a temptation here to say, oh, I know that the Taylor series for e to the x, that looks like e to the x is the sum k equals 0 to infinity of x to the k over k factorial, which is absolutely true. That is what e to the x equals. And so what's the temptation? Well, the temptation is, oh, they just made this one really easy because I could take my e to the x to the 3/2 minus 1, and what I'll do is everywhere I see an x, I'll put x to the 3/2 minus 1. So I have this is the sum k equals 0 to infinity of x to the 3/2 minus 1 to the k over k factorial. That's very tempting to do. It's true that those are equal. However, this part right here, this is not a Taylor series. So be careful. Why is it not a Taylor series? Well, because this has powers of x to the 3/2. You only want x minus 1. So we can't just do some simple manipulation. Well, if we can't do simple manipulation, we go old school, the definition, because we should know the definitions. So P2 of x is what? Well, it's saying find your really good second order approximation to your function. And the way you find it, because we're going around x equals 1, it'll be f of 1, I want to approximate the value of the function, plus f prime of 1 times x minus 1. This guarantees you also match the first derivative of the function at 1, plus f double prime of 1 over 2 x minus 1 squared, and this will guarantee you match the second derivative. And you don't have to go any further, because we only want the second order. So this says approximate these, to approximate I need these numbers, f of 1, f prime of 1, f double prime of 1. So I start with my function. F of x is equal to e to the power x to the 3/2 minus 1. F prime of x, well, we apply the chain rule. So chain rule says you take the original function, take the derivative. Well, the derivative of e to the x is e to the x. So keep the inside unchanged. So you get e times e to the power x to the 3/2 minus 1. Then I have to times this by the derivative of x to the 3/2 minus 1. Well, that's 3/2 x to the 1/2. So that's my first derivative. And then my second derivative, well, I'm going to have to do a product rule, and I'm going to have to do a chain rule. Now, product rule, the derivative of the first times the second. But I already know the derivative of the first because I did that in my first step. So I'm going to have e x to the 3/2 minus 1 times 3/2 times x to the 1/2 by the chain rule. Okay, that's the derivative of the first times the second plus the first, which is e x to the 3/2 minus 1 times the derivative of the second. Well, that's the derivative of 3/2 times x to the 1/2, which would be 3/4 x to the minus 1/2. The 1/2 comes down. Okay, so there's my function, my first derivative, my second derivative. Now, what do? I evaluate. I plug in 1. Now, the nice thing about 1 is a very easy number to evaluate at. 1 to a power is 1. So upstairs, I'll have e to the 1 to the 3/2 minus 1. That's e to the 0. That's 1. F prime of 1. Well, again, I'll have e to the 0 times 3/2. So that's 3/2. F double prime of 1. Well, I'm going to get 1 times 3/2 times 3/2. So that's 9/4. plus 1 times 3/4 times 1, which is plus 3/4. And 9/4 plus 3/4 is 3. And therefore, we can say P2 of x is equal to function at 1 plus f prime of 1, which is 3/2, times x minus 1, plus f double prime of 1 over 2. So I have the advantage. I can actually see what I wrote before. So f double prime 1 over 2 is another 3/2 x minus 1 squared. And that's the answer. 1 plus 3/2 times x minus 1 plus 3/2 x minus 1 squared. Done. Okay. Good. Good. How you doing? Okay. All right. I know you're missing The Secret Lives of Pets. It's your last chance to watch something at Cyclone Cinema. Okay. So we're almost at the halfway point, and yep, we're still going strong. Good. So here we go. Number 10. Suppose you have your function f of x is cosine 5x minus log of 1 plus 3x squared. And you're asked to do the following. Write f of x as a Taylor series centered at x equals 0. That's part A. And part B, use the answer from part A to find the 10th derivative evaluated at 0. So what do? Well, we could go to our definition and take all derivatives, but that takes a long time. It's better to use what we know. So in particular, we know a couple of things. For cosine, I'm going to use z for a moment, cosine z. That's equal to the sum, n equals 0 to infinity of negative 1 to the n, z to the power 2n over 2n factorial. So I know the Taylor series for cosine. I also know the Taylor series for log. So just a side note here, we'll rederive it. So sum of x to the n equals 0 to infinity is 1 over 1 minus x. So sum n equals 0 to infinity. I integrate both sides. X to the n plus 1 over n plus 1 is log of 1 minus x times a minus 1. Got it? So I have to compensate for the inside. And so, in particular, we have the following. If I move stuff around. So log of 1 minus z is equal to the sum, n equals 0 to infinity of minus x to the n plus 1. Let's just shift. Let's do ahead shift. Minus x to the n over n. Okay, so we have these two sums. All right. So let's now use these. So we use things that we've proven before because it makes things easier. One of our goals is we want to make things easier on ourselves. We don't want to work too hard. We want to work just the right amount. So how do we work just the right amount? So f of x is cosine of 5x minus log 1 plus 3x squared. Well, the way we work the right amount is we say, look, this is cosine, except I have 5x. So everywhere I have here z, I just put 5x. So this is the sum, n equals 0 to infinity of negative 1 to the n, 5x to the power 2n over 2n factorial. That's cosine 5x. Now, minus log 1 plus 3x squared. Actually, I can take advantage of the fact there's a minus here. I'll put minus log 1 minus z is the sum of x to the n over n. So minus log of 1 plus 3x squared, it's as though I have that this 1 plus 3x squared part here became this minus z part here. So that what I can do is I can say, aha, oh man, I am just full of typos. Okay, now we go. There we go. That should have been a z. So this becomes plus sum, n equals 1 to infinity of minus 3x squared to the n over n. So I'm adopting what I can figure out for the Taylor series for log to get this log of 1 plus 3x squared. Okay. It works, I promise. I'm not lying to you on this one. I haven't lied to you on any of them. So, all right. Well, so what does this become? Let's clean this up a little bit. This is the sum. N equals 0 to infinity. I have negative 1 to the n. 5 to the 2n. Well, 5 to the power 2n is the same as 5 squared to the n. That's 25 to the n. So I can write this as negative 25 to the n x to the 2n over 2n factorial. Plus the sum, n equals 1 to infinity. And here I have negative 3 to the n, x to the 2n over n. And now we're just about done. We see we have these two beautiful sums. We can go ahead and put them together. They match in their powers. They're both x to the 2n in both cases. The only thing they don't match is they don't match where they start. One sum starts at 0, the other starts at 1. But that's easy to fix. How do we fix it? Well, we just say pull off the n equals 0 term. And the n equals 0 term, plug in n equals 0, you're going to get negative 25 to the 0 is 1, x is 0 is 1, 0 factorial is 1. So that's 1. And then the rest of the terms can come together into one big sum. Sum n equals 1 to infinity of, grab the various coefficients, negative 25 to the n divided by 2n factorial plus negative 3 to the n over n times x to the 2n. And there's my part A. Write f of x as a Taylor series centered at 0. Okay, so we've done part A. Part B, which you can't see, but it's on your sheet, says, look, find the 10th derivative. Well, how do we find that? Well, we find that by saying this here, this is really the sum, if it's the Taylor series, of the kth derivative at 0 over k factorial x to the k. Because that's what a Taylor series does. So if I'm looking for the 10th derivative, what do I need? Well, look at k equals 10. So I'm looking for the coefficient of x to the 10. Now, let's be careful here. What does n need to be to get x to the 10? I need 5. So I'm going to plug in n equals 5. And if I do that, I see that the coefficient for the 10th power of x is negative 25 to the 5 over 10 factorial plus negative 3 to the 5 over 5. Now that will be equal to the 10th derivative at 0 over 10 factorial. So to finish it off, we just multiply both sides by 10 factorial. And so the 10th derivative evaluated at 0 will be equal to, multiplying both sides by 10 factorial. In the first term, the factorials actually cancel, negative 25 to the 5th power plus negative 3 to the 5th power over 5 times 10 factorial. And that's okay to leave the answer in that form, because that's the right number. You don't have to multiply it out. That's for something when you have a computer. The computer can do that. We just want to see you get to something of that form. Okay, number 11. This must be important because it's the halfway point. All right, or maybe it's not, I don't know. Suppose you have the function f of x is equal to e to the negative x over 2. And we're asked to do the following. Find the second order Taylor polynomial of order 2 for f of x centered at 0. Now this is not so bad. We can actually do this in a couple of different ways. For instance, one thing we can do is we know the Taylor series for e to the z. We know that e to the z is equal to the sum k equals 0 to infinity of z to the k over k factorial. And so e to the negative x over 2 would be equal to the sum k equals 0 to infinity of negative x over 2 to the k over k factorial, which you can clean that up. Sum 0 to infinity of minus 1 to the k x to the k over 2 to the k factorial. So we actually know the whole Taylor series for e to the negative x over 2. To find that p2, that's just the first couple of terms. The other option, of course, is go back to what we did on the previous problem, or at least 2 problems back, where we said, okay, take the derivatives, evaluate, take derivatives, evaluate, and there we go. So either way we do it, it's not very hard in this case, and so we get the following. So if I just read it off here, I would have the following. I'd have that this is equal to, plug in p2 of x. So I'm just plug in 0, negative 1 to the 0, x to the 0, 2 to the 0, 0 factorial. Everything is 1, 1, 1, 1. So that's 1. All right, plug in 1. I get negative 1 to the 1. That's a minus 1. There's an x, so I get minus x. 2 to the 1, that's 2. 1 factorial is 1. So that's minus 1/2 x. Plug in 2. Negative 1 squared, that's 1. X squared is x squared. 2 squared, that's 4. 2 factorial is 2. So this becomes 1 over 8 x squared. So read off the first several terms of the Taylor series. And part A, we're done. All right. Now, part B, this is getting into approximation. Or rather, I should say error estimation. So you can make approximations, and that's what we're doing oftentimes when we do these Taylor polynomials. But your approximation is only as good as your error estimation. Because you can say, well, the answer is 10. You say, okay, well, what's the error? Well, plus or minus 1,000,000. Not a very good answer. But if you say my answer is 10, and my error is plus or minus 1 over 100, okay, that's a good answer. So we want to make sure we can do good error estimation, which is what this problem is testing us on. Now it says find the best number for which the third derivative is bounded by m. Now, because we didn't find the third derivative, we should go ahead and find that. So we have f of x, that's e to the minus x over 2. F prime of x, that's minus 1/2 e to the minus x over 2. F double prime of x, that would be 1/4 e to the minus x over 2. So in other words, every time I take the derivative, the minus 1/2 comes down. And the third derivative says, bringing the minus 1/2 down again, that's minus 1/8 e to the minus x over 2. So I found my third derivative, and it says find the best. We'll talk about how to find the best, number m, so that the third derivative is at most m for all y between 0 and 2. So I'm looking at this function, negative 1/8 e to the minus x over 2. And I'm taking the absolute value, and I'm looking at x between 0 and 2. So the way you find the best is you say, what's the biggest this expression can be? Now, we know something about the exponential function. It has a nice shape to it. In particular, e to the minus 0 is what? It's 1. And as x increases, I'm having e to a negative power, which means I'm going to get smaller. So if I'm trying to make it the biggest number, so in other words, what's the worst case scenario? That's how you find m. Worst case scenario is it happens at 0, because the function I can see is decreasing. So the maximum it can get is at 0. So oftentimes, if we're asking you to find the best number, we'll give you a very simple function. Either it's increasing, or it's decreasing, or maybe it's like a sine or cosine, because they're always bounded between 1 and negative 1. There's something which will be very simple. So the biggest that this can possibly get between 0 and 2 is at 0. And so I can say that this expression here, this negative 1/8 e to the minus x over 2, is less than or equal to 1/8, which is what happens at 0. And this is the best I can hope for. I can't go smaller than that. All right, that's part B. So this is my m. Now, part C. It says, recall, you have this expression for error estimation. Now, I will tell you right now, in case you are getting nervous, that this expression here, you do not have to memorize. if we ask this kind of problem on the test, we will give you this formula. However, you need to know how to use this formula. So how do you use it? It's saying, look, I want to bound my function and my approximation. So P2 of x is an approximation. So I want to say, well, how good of an approximation is it? Well, the answer is you can bound it by this expression, m, which is the same m you would have found in part B, times x minus a to the n plus 1. Now, a is where we're centered at. We were centered where? Well, we were centered at 0. So in our case, a is 0. And n, well, what is n? N is what approximation you took. In our case, we're doing n equals 2, because we're doing the second order approximation. So we're doing n equals 2, a equals 0. So this is our a, and this is our n. Okay, so recall the formula. Use this bound to bound this difference between f of x and P2 of x. Now, this sounds complicated, but the truth is this is not meant to be complicated, because what you do is you straightforward apply the formula. So you say f of x minus P2 of x. You want me to move down or move up? One of them, right? Pick a side, pick a side. So f of x minus P2 of x. I'm applying this formula, which you can't see, but imagine that you had it written down on the sheet of paper that you got, because it was written down on the sheet of paper that you got. This is less than or equal to m times x minus 0 to the power 3 over 2 plus 1 factorial. So that's copying it down. Now m, we know, is 1/8. We can take it. That's part B. 2 plus 1 factorial, that's 3 factorial, that's 6. Finally, we're focusing on 0 less than or equal to x less than or equal to 2. I want a number. Why do I want a number? Because it tells me I want a number. My answer should be a number. So now I say, okay, well, what about this x minus 0 cubed? Well, what's the biggest that it can be? Because x is between 0 and 2, the largest it could be is what? Largest it could be is at x equals 2, which is 8. And so times 2 cubed, and you say, oh, perfect, look, 1/8 times 2 cubed, they cancel, and I get 1 over 6. So my error is I'm most off by a 6 over the course of the whole interval. In other words, any point I look at, I'm no more than 1/6 off. Now you might say, that's not very great, but I'll point out we only did a second order approximation. Computers, they can give us any order we want. Okay, good. All right. I am definitely going slower than I should. I apologize. I hope you're okay. Again, if you need to leave, I am not offended at all. All right. So, number 12. This one, I have to say, I really wish I could put it on the test, but I didn't feel I could get it past the other instructors. So we put on the review. All right. So suppose you have a function f of x, and it's defined to be the sum n equals 0 to infinity, x minus 2 to the n over 4 to the n. Perfectly valid way to say it. It's true, I can define my function this way. And now I want to find the Taylor polynomial for f of x centered at x equals 3. In other words, rewrite it in this format. Sum Cn x minus 3 to the n. Now, this looks like an almost impossible problem until you realize, wait a second, this part right here looks suspiciously geometric. What do I mean by that? Well, this is the sum, n equals 0 to infinity, of x minus 2 over 4 to the nth power. If I have something to the n and I'm summing that up, then by our basic sum formula for geometric sums, this is 1 over 1 minus x minus 2 over 4. Or this is 1 over, multiply top and bottom by 4. So actually, let me multiply top and bottom by 4. And then you get 4 minus 2 is 6 minus x. So this function is actually a really nice clean function, 4 over 6 minus x. Now, what do we want to do? We want to have it centered at x equals 3. Well, how do I do that? So I take 4 over 6 minus x, and I want to write it in terms of x minus 3. So how can I do that? Well, that's 4 over 6 minus, I'm going to put x minus 3 plus 3. I can do that. That's perfectly legal, which is 4 over 6 minus, think of the x minus 3 as a group, 6 minus 3, so 3 minus x minus 3. And what am I doing here? I'm trying to write things as x minus 3, because I'm ultimately trying to get into the form something with x minus 3 to a power. I'd really love it if this were a 1. If this part here were a 1, this 3, it would be fantastic. We would be so ecstatic because it would be exactly the right form to do a geometric sum. And so what we're going to do is we're going to make it a 1. And how do we do that? Well, we factor stuff out. I'll factor 4 out of the numerator. I'll factor 3 out of the denominator. And if I do, I'll have 1 over 1 minus x minus 3 over 3. So 4/3 times 1 over 1 minus x minus 3 over 3. And now we say, perfect, numbers are easy. And then this is exactly the right form for a geometric sum. 1 over 1 minus something. Okay, so this is 4/3 times sum 0 to infinity of the something x minus 3 over 3 to the kth power. Or, if you like, you can put the 4/3 inside, sum 0 to infinity of 4 times x minus 3 to the k, and downstairs I have a 3 to the k times another 3, and so I get 3 to the k plus 1. And that's my answer. 4 times x minus 3 to the k over 3 to the k plus 1. Okay, that's number 12. I like that one. Number 13. Okay. Should we skip those for a while? All right. All right, I'll do this one a little bit quicker here. I want to find the Taylor series for f of x equals 1 over 2x minus x squared centered at x equals 1. And the way I can do this is I can say, well, I'd really like to have something of the form x minus 1. Because if I did, life would be fantastic. And I say to myself, wait a second, x minus 1, because I have 2x minus x squared, but that looks a lot like 1 over negative x squared minus 2x. And x squared minus 2x is amazingly like x minus 1 squared. In fact, if I added 1 and subtracted 1, I would say, that looks like x minus 1 squared. And I like x minus 1 because I'm centering around x equals 1. So I say this is really equal to 1 over 1 minus x minus 1 squared. Because I can just, the minus 1 is where that 1 is coming from. Now you're saying, well, okay, so what? The point here is the sum n equals 0 to infinity, z to the n is equal to 1 over 1 minus z. It's impossible to do one of these tests without at some point seeing a geometric sum. This is my z. So this is the sum n equals 0 to infinity of x minus 1 squared to the n, or the sum n equals 0 to infinity of x minus 1 to the 2n. That's the answer. The sum of x minus 1 to the 2n power. It's seeing how can I rewrite things in terms of x minus 1. And when you can, it becomes really clean. And it works out very nicely. Now, that's because it's very convenient where we're set up. It might not be so convenient. So, for instance, you might have the following. Find the Taylor series for f of x equals 1 over 2x minus x squared, centered at x equals minus 1. Now you might say, well, how much could it make a difference, this minus 1? The answer is it's going to make a big difference. Because what I'm really looking for is I'm really looking for things that look like x plus 1, or if you will, x minus minus 1. X squared minus 2x is perfectly set up to produce x minus 1 squared. X squared minus 2x is not set up to produce x plus 1 squared, which is unfortunate. Now, in this case, I can't see a nice way to get everything in terms of x plus 1 in this part, but what I can say is I could rewrite this as 1 over x times 2 minus x. That's perfectly allowed. And you should start thinking about what are things I can do. Now, in this case, what's something I can do? 1 over x times 2 minus x, I can use partial fractions. So that's something over x plus something over 2 minus x. And now I clear my denominator. 1 equals a 2 minus x plus b times x. And I choose good values for x. Say x equals 0. I can conclude a better be a half. If I plug in x equals 2, I conclude that b better also be a half. All right, well, that's good. Works pretty well in both cases. So what do I have? I have that f of x is equal to 1/2 over x plus 1/2 over 2 minus x. Now we're almost done. We're almost done. Now what I do is I want to write everything in terms of x plus 1. So this is 1/2 x plus 1 minus 1. I'll come back and clean that up later. Plus 1/2, and again 2 minus x plus 1 minus 1. Well, in the first part, I can say I'll pull out a negative 1/2. And if I do that, I'll be left with 1 over 1 minus x plus 1. I say, perfect, perfect. That's exactly geometric. The negative comes from I want to negate the bottom. I really want 1 minus something. Now, in the second part, I have to be a little bit more careful here. Notice here, I have the minus x plus 1 already, but I have 2 minus minus 1. That's 3. It's really 2 plus 1, 3. So what I'm going to do here is I'm going to pull out 1/6. And if I do that, what's left? Upstairs I'll have 1. Downstairs I'll have 1 minus x plus 1 over 3. And now we're basically done because we have ready to go our geometric series. So this is negative 1/2, the sum from 0 to infinity, x plus 1 to the n, plus 1/6, sum 0 to infinity, x plus 1 over 3 to the n. And we can combine these together so that we can write it as one big sum. Sum 0 to infinity of negative 1/2 plus 1/6 times 1 over 3 to the n times x plus 1 to the n. Okay. I'm going a little bit quickly here because I want to get into a couple of other problems. All right. Use the Taylor series for f of x equals sine of x, centered at x equals 0, to write the integral from 0 to 1 of sine x over x dx as a sum. Well, how do we do it? We know sine of x is equal to the sum from n equals 0 to infinity of negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. Why? Because it's one of the things that we should know. We should know important series, and sine was an important series. So sine x over x, what do? I divide by x, which effectively takes out that plus 1. So sine x over x is the sum, n equals 0 to infinity, of negative 1 to the n, x to the 2n, over 2n plus 1 factorial. So the integral of 0 to 1 of sine x over x dx is equal to the integral over from 0 to 1 of the sum, n equals 0 to infinity, negative 1 to the n, x to the 2n, over 2n plus 1 factorial, because I can replace sine x over x with the sum. But the cool thing about sums is that we can interchange sums and integrals where it converges, and it happens that sine converges everywhere. And sine x over x will also thus converge everywhere. So this is the sum, n equals 0 to infinity, of negative 1 to the n over 2n plus 1 factorial times the integral 0 to 1 of x to 2n dx. Well, this is not a hard integral. Integral of x to 2n, 1 over 2n plus 1, x to 2n plus 1, evaluated from 0 to 1, and evaluate at 1, you get 1, evaluate at 0, you get 0, and thus you get that coefficient. So our final answer is the sum, n equals 0 to infinity, of negative 1 to the n divided by 2n plus 1 factorial times 2n plus 1. And that's the answer to the first part. Now remember, there's two parts. One, write it as an infinite sum. Here's the infinite sum. The other part is to approximate it. Well, to approximate it, we use the first couple of terms. So the integral 0 to 1 of sine x over x dx is approximately, we plug in 0. And we say we get negative 1 to the 0, which is 1. 0 plus 1 factorial is 1, times 0 plus 1 is 1. So 1. Then the next term will have a minus because it's negative 1 to the 1. So minus. Then I'm going to have n equals 1. That's 3 factorial, which is 6, times 3. 6 times 3 is 18. 1 minus 1 over 18. Next term, n equals 2. Negative 1 squared is positive. Downstairs, 2n plus 1. Well, n equals 2. That'll be 5. 5 factorial is 120. Times another 5 is 600. And so there's a nice approximation to the integral from 0 to 1 of sine x over x dx. It's actually a pretty decent approximation. All right. Well, we survived through the series. Chapter 10. All right, we're not done yet because there's still chapter 11. And if you need to go, again, I do apologize, I'm going slow, but feel free to go. I won't be offended. This will be posted online. You can look at it at your leisure. You have a full week. But let's go ahead and keep going. Everyone doing okay? Woo! All right. Let's hope you have that spirit when you're taking the test. Okay. I hope you enjoy it. I hope you enjoy it. A lot of thought went into it. Number 16. Find the tangent line to the polar curve r equals 1 plus 2 cosine theta at theta equals pi over 3 and theta equals 4 pi over 3. I don't know what this curve looks like. I don't have to know. I just have to find the tangent line. Now, to find the tangent line, it's kind of strange because lines are really more, they're not really polar, that's more Cartesian. But that's okay. So if I think of this here as my f of theta, r equals f of theta, then I have that x would be equal to f of theta cosine theta, and y would be my f of theta sine theta. Now, on a side note, you might be wondering, do I need to know my values for my trig functions? And the answer is you should know your basics. If you basically know what's in the first quadrant, your 0, your pi 6, your pi 4ths, your pi 3rds, and your pi halves, you'll be okay. But the other answer is you'll have your calculator. So if you don't remember, plug it in and see what you get. All right. Okay, so what do I want? I have to figure out the tangent line at theta equals pi over 3, theta equals 4 pi over 3. Well, this right here can give me my point, my xy. I also need my slope. So for my slope, well, what do? I'm going to take y prime of theta over x prime of theta. That will give me slope. All right. So what is y prime? Well, product rule. So you're going to get f prime of theta sine theta plus f of theta cosine theta. Downstairs, f prime of theta times cosine theta minus f of theta sine theta. All right, and we know what f of theta is. Of course, we can also note f of theta is 1 plus 2 cosine theta. F prime of theta would be negative 2 sine theta. So here we go. Theta equals pi over 3. I actually, to be honest with you, I don't know what the answer is. I haven't done this one yet. I hope it's not bad. Hope it's not bad. Fingers crossed. We go in. So, what do we get? Well, f of theta would be 1 plus 2 cosine pi over 3. Now, cosine of pi thirds is equal to a half. So I'm going to get 1 plus 2 times a half, which is 2. Okay, so that's pretty clean. But it says that my x is equal to 2 times cosine of pi thirds, which is a half. My y is equal to 2 times sine of pi thirds, which is square root of 3 halves. And therefore, my point is at 1 comma root 3. So there's my point. My slope will be, well, let's figure that out. F prime of theta, let's do a quick computation. That's negative 2 sine pi thirds, which is equal to minus root 3, because sine of pi thirds is root 3 over 2. All right, so we plug it in. Slope, which you can't see. Now you can. We plug in our values. F prime would be negative root 3 sine root 3 over 2 plus f of theta, 2 times cosine, which is 1/2, over f prime theta, negative root 3 times cosine, 1/2, minus my f of theta, which is 2 times sine, root 3 over 2. Now, what do we get? Well, upstairs we get minus 3 halves plus 1. Minus 3 halves plus 1 equals minus a half. Downstairs, what do we get? Well, they both have root 3. I can go ahead and factor root 3 out. And I'm going to get minus a half. Okay, so there's a minus a half there and a minus there. So let's go ahead and plot a minus as well. Then I'm left with a half plus 2. A half plus 2 is 3 halves. Minus minus cancel. The 2's cancel. So we end up with 1 over 3 root 3. Or if you like, multiply top and bottom by root 3 over 9. Now, do you have to multiply? No. You can leave it as 3 over root 3. It's okay. It's okay. But now I have point, I have slope. So my line would be y equals my slope, root 3 over 9, times x minus my x coordinate plus my y coordinate. All right. So again, this is the formula y equals slope, x minus your x coordinate plus y coordinate. All right. That is half the answer. Nice. Now, why is it half? Because we have to do it a second time. 4 pi thirds. All right. 4 pi thirds. Well, what is my expression? I have 1 plus 2 cosine of 4 pi thirds. Well, cosine of 4 pi thirds is? Cosine 4 pi thirds is? Negative a half. This is 1 plus 2 times negative a half, also known as 0. Which says, where's my point at? If you have your radius is 0, your point is? So this, remember, this is r. r equals 0. That's the origin. So I'm going through the origin at that point. All right, so now I know my point, 0, 0. That's great. That means my slope is y equals mx. As soon as I figure out m, I'm done. Okay, so let's do my slope. So, slope. Slope will be what? Well, again, you probably can't see it because it's way up here, but I'm just going to apply the same formula. So, I should figure out what is f prime of theta. Well, f prime of theta, that would be minus 2 sine of 4 pi thirds, which will be equal to root 3. Because sine of 4 pi thirds will get us to negative root 3 halves. So a minus cancel. So my slope is f prime of theta, which is root 3, times my sine, negative root 3 over 2, plus my f of theta, which is 0, times my cosine, which is negative a half, over my f prime theta, root 3, times my cosine of theta, which is negative 1/2, minus my f of theta, which is 0, times my sine, which is minus root 3/2. Now, the nice thing is the zeros you can ignore. The root 3 over root 3 cancel nicely. The 2's cancel. The minuses cancel. Almost everything cancels. One thing that doesn't cancel is the root 3. That's your slope. So go through the origin. My slope is root 3. So my line is y equals root 3x. And that's the other line. There are my 2 lines. 2 lines, and I'm done. All right. Well, so find the tangent lines. Number 17. Here we go. This one's a good one. Find the length of the parametric curve 7 cosine t minus cosine 7t, 7 sine t minus sine 7t, for 0 less than or equal to t less than or equal to pi. This is the actual picture. It's kind of cute, kind of like a cloud, nice and fluffy, just like our calculus test. It's a nice, fluffy test. You know, be in your happy place when you take that test. And there's a hint here. It's kind of a bizarro hint, but okay, whatever. Who knows? Maybe it's useful, maybe it's not. I don't know. But length of a parametric curve, we should know that formula. So length is equal to the integral of a to b square root of x prime of t squared plus y prime of t squared dt. So that's just one we should know by heart. Now, x and y, what are those? Well, that's my x, and that is my y. So it's the x part and it's the y part. So I would strongly suggest, if you have these types of problems, to sort of build up to it. And oftentimes when you have a lot of things with sines and cosines and you have to square things, it's going to get messy and you're going to expand and you're going to get really depressed. It's like, oh my gosh, this is never going to simplify. And then wonderful trick things happen and things simplify nicely. But be patient and have faith. So x prime of t would be, taking the derivative, negative 7 sine t, and then it would be plus 7 sine 7t. Y prime of t would be 7 cosine t minus 7 cosine 7t. So there's lots of 7s here. That's okay. Now let's look at the squares, because I want x prime squared and y prime squared. So x prime squared would be equal to, I'm going to square this out. So you square the first term, 49 sine squared. And then I'm going to have the cross terms. So what do I mean? 2ab. So this is, think of this first thing as my a squared, minus 2ab. So 2 times 7 times 7, well, I'll say 2 times 49 because I don't want to do 2 times 49 in my head. I'm just kidding. It's 98. I know that. Okay. Sine t, sine 7t. And then the second term, or rather the b term, b squared, 49 sine squared 7t. All right. That's x prime squared. Already, you're getting nervous. You might say, he's never going to get this to work out nicely. Well, I hope I do. I don't know. We'll find out. Okay, y prime squared. Here we go. Similar process. 49 cosine squared, then minus 2 times 49 cosine t cosine 7t plus 49 cosine squared 7t. Similar process. No big surprise. Now, let's add them up. So I have x prime squared plus y prime squared. 49 sine squared plus 49 cosine squared becomes 49. Then I have minus, 2 times 49, I guess. Okay, I'll go, all right, that's 48. But then I have, sine of t, sine of 7t, plus cosine t, cosine 7t. Well, okay, we'll come back to that in a second. Then on the back end, 49 sine squared plus 49 cosine squared becomes 49. That's great. The only problem is we have this part. We say, how could they do this to us? If only they had given us a hint as to how to handle that. Notice there's a nice hint. If you have something sine, sine, cosine, cosine, you can rewrite it as a single cosine. So if we apply the hint, this is equal to cosine of 7t minus t, also known as cosine of 6t. So what do we have? We have that x prime of t squared plus y prime of t squared. Well, 49 and 49 make 98, so there's a 98 there as well. Okay, let me write this as 49 times 2 minus 2 cosine 6t. That's true. That's true, because I factor out of 49. 49 and 49 is the 2. Now, I want to take the square root of that. That looks like it's a messy thing to take the square root of. But then we remember that we did all these power reduction facts, and there's a nice power reduction fact that says, on a side note here, we should change colors. Just, that's our mental side note, different color. We have this sine squared was equal to 1/2, well, let's change it to sine squared theta, 1/2 minus 1/2 cosine of 2 theta. Which says if I do two things, let's multiply both sides by 4. 4 sine squared of something is equal to 2 minus 2 cosine of something. Now what's the something? Well, if I wanted 6t, replace theta by 3t, I'd get 6t here and 3t there. So that this part right here is really a nice perfect square. Okay, so we're almost done. We've actually done all the hard part, which feels amazing because it feels like we haven't started yet. But here we go. The length is equal to the integral from a to b, in our case, 0 to pi, because we're going between 0 and pi. So the length is the integral from 0 to pi of the square root of x prime of t squared plus y prime of t squared dt, which is the integral 0 to pi of the square root of this part right here. But now we know how to take the square root. That's square root of 49 is 7. Square root of 4 is 2. Square root of sine squared is the absolute value of sine. Okay? And that's absolutely true. Now, can I drop the absolute value? What? Yes. Oh, the answer is no, you can't drop the absolute value. Why? Because sine could be actually negative here. Remember, you could say, look, if it was just sine of t between 0 and pi, you're safe. Because it's sine of 3t will actually go negative in between 0 and pi. And so you should be like, dang it. But you know what sine of 3t will look like. It actually will have a very nice shape. It'll look like this. So, because of the absolute value, this part that would have been negative between what I would call pi thirds and 2 pi thirds became positive. However, it's going to behave in a very predictable way. So, this is, if we're careful and we don't forget that it can be negative, we say, look, I really just have to know what it does between 0 and pi thirds and then multiply by 3. So if I do that, 7 times 2 times 3, that's 42, integral 0 to pi thirds. Now I can drop the absolute value. All right, integral of sine of 3t. There's a negative, right? Good. Okay. It's late, I know. 42. I'm going to have to divide by 3 to compensate for the 3 there. 42 divided by 3 is 14. And then we're going to have integral of sine negative cosine. From 0 to pi thirds, well, plug in pi thirds. Cosine of 3 times pi thirds, that's minus 1, but minus 14, so that's 14. Oh, you can't see that. That's 14 minus 14, and which gives us a final answer of 28. So the answer is 28. Okay, good. If we had not followed through, what would have happened? Well, we would have gone not 28. That's what would have happened. Well, we don't want to get not 28. We want to get the right answer. Okay, all right. Oh, we just hit the hour and 45-minute mark. Okay, keep going? Well, I'm going to keep going. Okay, it's up to you if you want to stay. All right, so let's try a nice fun one. Find the surface area, which results from rotating the parameterized curve 7 thirds t cubed plus t, 2 thirds 2t squared plus a fourth to the 3 halves, where t goes between 0 and 1 around the y-axis. Okay, so what do? Well, we know this is our x, and we know this is our y. Okay, what's surface area? Surface area, there's a nice formula for that. It's the integral a to b of something, and the something is where we're spinning it around, times our length. And our length, that's what we were just doing. That's our x prime of t squared plus y prime of t squared square root dt. Okay, so that's the length. Now, in this case, we're going around the y-axis. So if we're going around the y-axis, our radius is the distance to the y-axis, which is x of t. And, of course, I almost forgot the 2 pi. Very embarrassing. Don't forget the 2 pi. Because, we want all the points. That should be your goal. Get all the points. All the points. Okay. So let's set up our integral. Let's see. Let's work on the length part for a moment. X prime, well, take the derivative. That would be 7t squared plus 1. Y prime, take the derivative, 2 thirds times 3 halves. Okay, that's 1. That's nice. So it'll be 2t squared plus 1/4 to the 1/2 power times 4t. So x prime squared plus y prime squared then becomes 7t squared plus 1 squared plus, if you square this, you'll get 2t squared plus 1/4 times 16t squared. All right, well, expand. 49t to the 4th plus 14t squared plus 1. Multiply through. You'll get 32t to the 4th plus 4t squared, or 81t to the 4th plus 18t squared, 14 plus 4 plus 1. And by magic, or I should say, as though they wanted us to be able to do this without a calculator, it will become a nice square. Okay, so we're now ready to work on surface area. So our formula for surface area. This will be the integral 0 to 1, because I can read off my bounds. 0 to 1. 2 pi. My x of t will be 7 thirds t cubed plus t. That's my x of t. My length is going to be the square root of all that, so that's 9t squared plus 1 dt. From here, it's just computation, and I don't know if we really need to do computation, but if we did, this would be 2 pi integral 0 to 1. We'd multiply things out. For instance, 7/3 times 9. Well, 3 goes into 9. So that's really 21 t to the 5th. Then you get plus 7/3 t cubed. Then you'll get another plus 9 t cubed. And then you get plus t. And if you wanted to, you could observe that 7/3 plus 9 will get a common denominator of 3. And that's 7/3 plus 27/3, which gives you 34/3. So we have that this is 2 pi integral 0 to 1 of 21 t to the 5th plus 34/3 t cubed plus t dt, which is, if we carry this out, 2 pi times 21 t to the 6 over 6 plus 34/3 times t to the 4th over 4 plus 1/2 t squared. Evaluate from 0 to 1. And when you plug in 0, the zeros drop out, everything drops out, plug in 1. So let's see, let's clean this up. Okay, 21 goes into, well, 6 goes into 21. They have a common factor of 3, so that leaves 2 and 7. Then I'm multiplying the 2 pi through, so that's 7 pi from the first term. Here in the second term, I have this 2 coming in. So there's a 2. There's another 2 from the fact that I can write 34 as 2 times 17. So I have 2 times 2 going into 4. So the 2's cancel. So I'm left with a 17/3 pi. And then finally I get a 2 pi times a half, which is just a normal pi. So 7 pi plus 17/3 pi plus pi. Well, that's 8 pi plus 17/3 pi. That's 24 pi plus 17/3 pi, which is 41 pi over 3. Okay. All right, so there's a surface area. All right, now another one, the surface area. This one's a little bit different. It says find the surface area, which results from rotating this curve. But now, what's different? Well, it's going to go for a very long time, between 1 and infinity. Are we going to be intimidated by this infinity? Hopefully you didn't say yes. You should say no. It's the same idea. Same idea. No problem. No problem. So our surface area is going to be very similar to what we had last problem. So surface area is the integral a to b, our 2 pi, times where we're spinning around is the x-axis. So now our distance is y of t. So in other words, the distance to the x-axis, that's your y-coordinate. Then you have the square root of x prime squared plus y prime squared dt. So let's focus on sort of breaking this down. So x prime, well, that's 1 over t minus 1 over t squared. Y prime would be, take the negative 1/2 down, so that would be minus 2 t to the minus 3/2, or if you like, minus 2 over t to the 3/2. Now these are weird derivatives, but that's okay. Let's find out what happens. Now, if I take x prime squared plus y prime squared, that's 1 over t minus 1 over t squared squared plus negative 2 over t to the 3/2 squared, which is, now we square, 1 over t squared, the cross terms, minus 2 over t cubed, plus 1 over t to the 4th. Now what do we get here? Well, negative 2 squared is 4, t to the 3/2 squared is t cubed. And you say, that's interesting. It's almost as if they had planned for that to match, because we did. We did. Okay, so this is 1 over t squared plus 2 over t cubed plus 1 over t to the 4th, which you should say, that's almost like what we had before, except a plus in the middle, which means this is really 1 over t plus 1 over t squared squared. So our x prime squared plus y prime squared is clean, very clean. Perfect, perfect. So now we're ready to do our computation. So switching colors to start our computation. Surface area is going to be the integral. Our bounds are 1 and infinity. So 1 to infinity of what? Well, 2 pi, our y of t, 4 times t to the minus 1/2, times the square root of x prime squared plus y prime squared, which is the square root here, which is 1 over t plus 1 over t squared dt. All right, let's move that up. So let's clean this up. The 2 pi times 4, that's 8 pi. 1 to infinity. I can multiply the t to the minus 1/2 through. If I do that, now remember, this is really 1 over t to the 1/2. This is t to the minus 1. So this will become t to the minus 3/2. So t to the minus 1/2 times 1 over t is t to the minus 3/2 plus t to the minus 5/2 dt. Okay, so that's expanding through. All right, we're almost there, almost there. So we get 8 pi, we integrate. Integral of t to the minus 3/2, I add 1. That gives me t to the minus 1/2. Then I flip that over, minus 2 t to the minus 1/2. Over here, add 1, t to the minus 3/2, I flip it. So that becomes minus 2/3. Evaluate from 1 to infinity. And when we mean at infinity, we say, okay, what happens as t goes to infinity? Well, I have negative exponents, so it goes to 0. So I get 8 pi times 0 minus, plug in 1. Well, 1 to a power is 1. So minus 2, minus 2/3. Okay, we're really close. Minuses all go away. 2 plus 2/3 is also known as 8/3. 8 pi times 8/3 gives us a final answer of 64/3 pi. And that's it. 64/3 pi. Just what we thought when we started. All right, good. So just because there's an infinity involved does not mean the answer is infinity. It could be finite. Could be finite. All right, find the length of the polar curve. So we did a length of problem before, but this is a length of a polar curve, which is slightly different. Okay, so that's a different formula. Different formula, so we should know the formula. So if this here is our f of theta, then length is the integral a to b square root of f of theta squared plus f prime of theta squared d theta. This is my a and my b. It's actually very similar to what the formula was before. In fact, if you set x of theta equals f of theta cosine theta, y of theta equals f of theta sine theta, and you run it through, it's the same thing. But I think it's probably easier just to memorize this. Okay, so let's make some notes. Well, we don't need to make notes. Let's just jump right in. Integral 0 to 3 pi. Square root. Okay, f of theta. Well, I just write it down. Cosine cubed 1/3 theta squared plus the derivative. Well, taking the derivative, I'm going to bring down the 3, cosine squared 1/3 theta. Then I'm going to times it by the derivative of cosine, which is a negative sine 1/3 theta. But then I keep going because there's still one more layer of my onion I have to peel through, times 1/3 squared. All right. Now this looks messy because it is, but let's unmessify. There's a 3 and a 3, so those will cancel. Nice. If I write down what I now have 0 to 3 pi square root of cosine to the 6 of 1/3 theta. And here I'm going to get cosine to to the fourth 1/3 theta times sine of 1/3 theta. Sine squared, excuse me, because I'm squaring. Now, here we say, well, what do they have in common? The answer is they both have cosine to the fourth. And if I factor out cosine to the fourth, I'm left with cosine squared plus sine squared. And cosine squared plus sine squared is also known as 1. And so what's left? Well, the square root of cosine squared, which says this is the integral of 0 to 3 pi of cosine squared 1/3 theta. Now, do I need an absolute value? No, I don't need absolute value, because cosine squared can never be negative. It's a square. All right, so I just have to integrate cosine squared. But I know how to integrate cosine squared because I was a good student. I memorized my power reduction rules. All right, be the good student. 0 to 3 pi, this would be 1/2 plus 1/2 of double the angle. So we're almost done. So we get 1/2 theta plus, if I integrate cosine, that's going to be sine. The angle in the inside will be the same, but what will be the coefficient in front? Well, this one you have to think about. The answer is 3/4. 3/4. So 1/2 times 3/2, because I have to flip the inside. And then I'm going to evaluate from 0 to 3 pi. Well, it looks messy, but what happens? Plug in 3 pi. 1/2 times 3 pi is 3 pi halves. Then I plug in 3 pi. 3 pi times 2/3 is 2 pi. Sine of 2 pi is 0. Plug in 0. 1/2 times 0 is 0. Sine of 0 is 0. So that's the answer. 3 pi halves. Done. Good. I feel like we're getting close. Okay. 21. Find the area inside r equals sine 2 theta and outside r equals 1/2. Now, on a side note, you may be wondering the following. Will we have to graph anything in polar coordinates? The answer is no. We're not going to test you on graphing, which means if we ask you a question about finding the area in curves, we'll actually hand a picture to you. So don't worry about, oh my gosh, what if I don't have the picture? You'll always have the picture. Now, my advice on these problems is just to say, look, let's find one piece. So I'm going to focus my energy on finding this one piece, and then I'm going to multiply my final answer by 4. So what do? Well, I need to set up my integrals, which means I need to find my bounds. So I need to find these angles of intersection. So to find the intersections, I set 1/2 equal to sine of 2 theta. And I say, well, when does 1/2 equal sine of 2 theta? Now, this is not so bad. We know the answer. Sine of pi 6 equals 1/2. So that tells me 2 theta would be pi 6. We also know that the next time that I get sine as 1/2 would be pi minus what I had. So my other angle is 5 pi 6, meaning that theta is going to go from pi over 12 to 5 pi over 12. So this is an angle of pi 12ths. This is an angle of 5 pi 12ths. Okay, so now I know my angles. I also know that my area is equal to the integral from my starting angle to my ending angle, 1/2 of the outer curve squared minus the inner curve squared d theta. So that's my generic formula for finding area in polar. So we're ready to set it up. So area is equal to the integral pi over 12 to 5 pi over 12. Now, I have to remember I'm going to multiply by 4. So I'm going to put a 4 here. That's my 4 because I'm only finding one of the 4. So now I have my 1/2. That's the 1/2 is part of the area formula. The outer curve is the sine curve. So sine squared 2 theta. The inner curve is the 1/2. So minus 1/2 squared, which is 1/4. Now sine squared, I need to change that. I change that by remembering I have my power reduction. So sine squared is 1/2 minus 1/2 cosine 4 theta. So if I multiply through by the 4 here, so I'm going to have 4 times 1/2 is really 2. Then I multiply that through. So I have the integral pi over 12 to 5 pi over 12. Okay, 4 times 1/2, that's 2, times the inside, so that's 1 minus cosine 4 theta, and then minus 1/2, or integral pi over 12 to 5 pi over 12 of 1/2 minus cosine 4 theta, d theta. Now, you might be nervous. I don't know the angles for pi 12, so you don't have to. You don't have to. Don't worry. Keep going. So what do we get? This is 1/2 theta minus 1/4 sine of 4 theta. And then I'm going to evaluate from pi over 12 to 5 pi over 12. So this will be 1/2 times 5 pi over 12. So that's 5 pi over 24 minus 1/4 sine, okay, doing some math here, 4 times 5 pi over 12, that's sine of 5 pi thirds. We'll go back to that and talk about what that is. Minus 1/2 times theta, so that's pi over 24, and then minus 1/4 sine of pi 12 times 4 is pi thirds. And I'm running out of space on the side. Okay. All right, so this is almost done, almost done. 5 pi over 24 minus pi over 24, that's 4 pi over 24, which gives us a pi over 6. Now, sine of 5 pi thirds. Well, first off, pi thirds is up here. The sine is at root 3 over 2. 5 pi thirds is the same as minus pi thirds. It's straight down. So this is 5 pi thirds. It's a pi third short of a full revolution. So the sine is minus root 3 over 2. So that's the sine values there. So we're going to have minus 1/4 times minus root 3 over 2. And then here, minus minus is plus. So plus 1/4 times root 3 over 2. So those minus minus plus plus. So there's 2 of those, which gives us pi over 6 plus root 3 over 4. And that's our answer. Pi over 6 plus root 3 over 4. Good. Done. Done. All right. Wow. You're really hardcore. You're sticking there till the end. Good for you. Good for you. Okay. All right. Let's see. Number 22. We've made it this far. We might as well finish it up. Find the area in the shaded region below for r equals sine of 1/3 theta. So here's kind of a strange region. If you follow what happens, if I start with theta equals 0, I'm actually at 0. So I start at the origin, and then as I move, I'm going to increase. So this portion here, this right here is the theta going between 0 and pi over 2. Now that's good to know. And then once I hit pi over 2, then I'm going to keep going. And so what happens here is from pi over 2 to 3 pi over 2, I'm this portion. So this is 0, less than or equal to theta, pi over 2 less than or equal to theta less than or equal to 3 pi over 2. And then I know I continue and so forth and so on. Now, because of the 1/3, it throws things a little bit out of whack. We actually end up tracing this curve in a slightly different way than usual. So what I would recommend is just to say, look, let's think about it as two things. We take a full half part here, and then we subtract out this little tiny inner piece on the inside. So if I did that, take the big part, subtract the little part, that'll give me what I need. So that's my mindset, is I'm going to say, okay, find the big part, subtract the little part. So the big part, the way I can find that is the following. I'm going to integrate pi halves to 3 pi halves of 1/2 of sine squared 1/3 theta, d theta. Now, this is not quite the whole. I really should do what to this? I really should times by 2. So if I just did 1, that would find half of the side, times by 2 to find the whole part. The small part, well, similar setup. I'm only going to find half of it double. So 2 times 1/2 sine squared of 1/3 theta, d theta. But now my bounds are 0 to pi halves. And I'm going to take my answer, my area, is the big part minus the small part. So the nice thing is these are very similar integrals. In fact, they're the same integral. They're just different bounds. Okay, so let's note for just a second. Well, let's go ahead. We'll do the big part first. So this will be pi halves to 3 pi halves. The 2 times 1/2 becomes 1. Sine squared, we use power reduction. So this will be 1/2 minus 1/2 sine of 2/3 theta, d theta. Oh yeah, you're right, it's cosine. I'll tell you, that's why we only make the test 2 hours and not 2 hours and 20 minutes. Because after 2 hours, your mind just shuts down. So that's, okay, thank you. All right, so this will become 1/2 theta, and then integral of cosine is a sine, and this will seem really familiar, 3/4 sine 2/3 theta. And evaluate from pi halves to 3 pi halves. Well, let's go ahead and evaluate. 1/2 times 3 pi halves, that's 3 pi over 4 minus 3/4. So 2/3 times 3 pi halves is pi. Oh, well, that's nice. And sine of pi is 0. Okay, subtract 1/2 times pi halves, that's pi fourths, minus 3/4 times, well, I take 2/3 times pi halves. 2/3 times pi halves, the 2's cancel, that's pi thirds. Sine of pi thirds is √3 over 2. Okay, so that term is gone. 3 pi fourths minus pi fourths, that would be pi halves, then minus makes plus, plus 3√3 over 8. That's the big. The small, okay, similar integral. Only difference is my bounds. Now I go 0 to pi halves. I'm already happier because I see a 0. Whenever I see a 0, I'm a very happy mathematician because 0 is such a lovely number. It's a number you could take home to meet your parents. Mom, Dad, I met this lovely number at university this semester. You're going to love her. Okay. All right. So we integrate. Hopefully this time, doing it correctly again, well, we don't even have to think. We just copy what we did before. Okay. So 1/2 theta minus 3/4 sine 2/3 theta from 0 to pi halves. Okay. Plug in pi halves. 1/2 times pi halves is pi fourths. then minus 3/4 times sine of pi thirds. Well, what's sine of pi thirds? Well, we know that. Square root of 3 over 2. That's sine of pi thirds. All right. Now I have to subtract. Evaluating at 0, that's easy. Everything evaluates to 0. Okay, so final answer. Well, we're going to take big minus small. So pi halves plus 3 root 3 over 8. Subtract pi fourths. And now notice here, what will this be? It'll also be minus 3 root 3 over 8, because they multiply together. Minus minus makes plus, and so what do we end up with? Pi halves minus pi fourths is equal to pi over 4, 3 root 3 over 8 minus minus 3 root 3 over 8. That's really going to become plus 3 root 3 over 4. Done. Done. Okay, so that took half hour longer than I wanted. Oh, thank you, thank you, thank you. I'll be here all week. So, parting thoughts. Look, I know this looks intimidating. You're probably thinking a lot of these problems were harder than you want. I try to make problems on the practice problems a little bit more difficult than the problems on the test, because I think that's better for you. There are plenty of problems. These are some of them. There will be more problems throughout the week. Keep practicing. If you practice, you can do it. I promise you. I have made sure that every single idea that you need to answer problems on the test have shown up in the practice problems. There's not going to be some like, oh my gosh, I never saw this. You will have seen it. I promise. I promise. Practice these problems. Practice more problems. The more you practice, the better off you are. You'll be okay. It'll be fine. All right. So good luck. And we'll see you next week.